In this video, I'll be talking about work energy theorem. Now, suppose you've got a car standing somewhere with an initial velocity of, in fact, let's not say the car is standing. Suppose the car is moving at a constant velocity of, say, 5 meters per second. Now, when this car is moving at a constant velocity of 5 meters per second, it means that constant velocity means that the net force is zero because there is no acceleration. So there's no change in velocity. So that's okay. And if you were to calculate the work done on this car, the work done would subsequently be zero because the net work done will be zero because the net force is zero. So that's okay. We can deal with that. But then imagine this guy decides that, you know what, I'm getting late for where I'm going. I need to be in town by 5, and let me just put my foot on the accelerator. And then he decides to speed up, and he increases the velocity to maybe 10 meters per second, and over a certain distance, which we can call also our displacement. Now, if from this point to this point increases the velocity by 10 meters per second, it means that there has been a change in velocity. And if there's been a change in velocity, there's been acceleration. And if there's been an acceleration, it means that there's been some net force exerted on this car in the direction of the motion of this car, in the plane of this car. Now, if there's been a change in velocity, it also means that there's been a change in kinetic energy, because kinetic energy is EK is equals to half of mv squared. So this parameter has changed, the velocity has changed, so it means that there's been a change in velocity. And if there's been a change in velocity, there's been subsequently a change in the kinetic energy. Now, what does this really mean? We've got the equation of motion, Vf is equal to Vi plus 2 change in x. So this talks to this talks to Newton's second law. This talks to Newton's second law. Newton's second law. When you see acceleration, when you see a change in velocity, you know that there's a net force. And if we express the Newton's second law in terms of the force, let me make this guy a bit smaller. In terms of the force, Newton's law becomes F net is equals to ma. And what we really want to do here is we want to reformulate the Newton's law in terms of work, in terms of energy, so that we can see where the work energy theorem comes from. So let's look at this equation, this equation of motion. If we make A the subject of the formula, the equation becomes A is equal to Vf squared minus V squared over 2 change in x, because this guy comes onto this side and then becomes negative, and ultimately you divide both sides by 2 multiplied by a change in x, so that you make a, you expose a and make it the subject of the formula. Now what happens in this situation is you could take this a, you could take this a, you could take this a and substitute it here. You could take this a and substitute it here. Remember, what we're trying to do is we're trying to reformulate Newton's second law in terms of work and energy, so that we can see where the work energy theorem comes from. So let's do that. If you substitute a here, you get F net is equal to m into Vf squared minus V squared over 2 change in x. So if you do a cross multiplication, mathematically you know that this is the same as over 1, and you can do a cross multiplication whereby 1 will multiply the numerator and this 2 multiplied by changing x will multiply the numerator this side. So you will have f net multiplied by 2 changing x is equal to m into Vf squared. So this, when you look at this is equal to change in V squared, because it's final velocity squared over initial velocity squared. That becomes change in, and then you can re-express this as F net is times change in x, and you can divide then both sides by 2, and this 2 will cancel this. You'll then have here, you'll have F net times change in x is equal to 1 over 2 m change in V squared. So we know that kinetic energy is half of mv squared, then half of m change in velocity squared will be change in kinetic energy, and then F net times change in x, force times displacement is work. So this will be the net work done. Okay, let me just write it properly. So this will be the net work done. The net work done. So we can now say that the net work done is equal to the change in kinetic energy, and this is our work energy theorem. It states that the net work done on an object is equal to its change, in kinetic energy from this point. We call this point A, point B. From this point A to this point B, the net work done by all the forces acting on this car will be equal to the change in kinetic energy, and that is the work energy theorem. And we're going to do a couple of examples in the next video just to demonstrate how it works with in the real world or with imagined questions. Stay tuned.